So if we have series resonance, series impedances like this, yeah, resistance in series with capacitance in series with inductance. So we have then the impedance is an addition of each of the impedance due to those passive components. Yeah. So the Z as a function of j omega will be equal to R plus j omega L plus 1 over j omega C. R is not a function of omega, it's only the L and C, yeah, which will cause an impedance that is a function of the omega here. So this becomes the real component of the impedance, and this part becomes the imaginary component of the impedance, or we call it as reactance. Okay, when now at the reactance, when omega L is equal to 1 over omega C, like this, so we know that this will be equal to 0. Okay, this is equal to 0. So the imaginary part of this impedance is equal to 0. So the impedance only has active only have real component, which is the resistance. So that is the condition of resonance, yeah. Or the frequency where this could happen when omega L equals to 1 omega C is called as the resonance frequency. So omega 0 equals to, so this omega L is multiplied with this one, omega C becomes omega square C, omega square LC. Omega stays here in the left side, so omega square equal 1 over LC, so omega 0 equals to 1 over square root of LC. So the impedance at omega 0, at j omega 0, will be equals to R, because omega L equals to 1 over omega C. Omega L minus 1 omega C equals to 0. This is what we call as the resonant frequency, and the Q, the quality of the resonance, or the quality factor of the resonance, is defined as the ratio between the omega 0L towards the R, yeah, or this impedance, the ratio, yeah, or the ratio of the impedance at the L compared to the R, and the ratio of the impedance at C compared to R, yeah, or omega 0 L over R, or equal to 1 omega over omega 0 C divided by R, 1 over omega 0 CR here. So from here, then the quantity is equal to 1 over R square root of LC. Where does it come from? Let's try to derive it. So for example, here omega 0, we know that omega 0 is 1 over square root of LC. So Q here equals to 1 over R. This L divided by square root of LC. Okay, and when so this is equals to 1 over R square root of L square divided by LC. So then Q equals to 1 over R square root of this cancel L over C. Okay, so this is the same as this formula. Yeah. Q equal to 1 over R square root of L. If we derive from here, that will be equal also 1 over omega 0 is 1 over square root of LC. This is CR. Okay. So this equals to then this goes to R square root of LC divided by CR equals to square root of LC divided by square root of C squared R. So this cancel, this become 1, and this is also cancel. So it become 1 over R square root of L over C. Yeah, we have the same result. Okay, so these are the the definition of quality factor as a function. It is a function of the resistance and the function of L and C. Okay, so this is the plot of omega. So omega at the resonance frequency, omega 0 here, then the impedance will be at its the magnitude of impedance will be at its minimum and is equal to the value of the resistance. And after that, omega, when the omega is increased, then we will have also another the impedance will also increase. Below the omega 0 also the impedance will also increase here. So this, when omega is less than omega 0 like this, it means what does it mean? Then the voltage is more towards the capacitance, like this in the phasor diagram. When omega equals to omega 0, the voltage at the resist, the voltage here across all the series passive components will be equals to VR. When the omega is larger than omega 0, then it is more towards inductive voltage here. The VL, the voltage across the L, will be larger than the voltage across the capacitance. Okay, so that's why it is more inductive circuit when the omega is larger than omega 0. Now we study about resonant circuits. So these are circuits with very special frequency characteristic, and resonance is a very important physical phenomenon. So in many physical, as you know that we are studying electric circuit, basically we do not only apply electric circuit modeling only for electrical network or RLC. The same modeling actually can be used for mechanical system and maybe for other system as well. Only that then we need to draw an analogy between spring, for example, with watt electrical component, then damper with what electrical component, then what else? Mesh with what electrical component. But they will form the same circuit model. And similar like in the electrical network, the same resonance could also happen in the mechanical domain. When there is a mechanical resonance, then usually it will have a the vibration will be very high in that particular mechanical system. So that is why here it is stated that resonance is very important physical phenomenon, and it does not only happen in electrical circuit, it also happens in mechanical circuit. So with time later, the more you learn about the system in nature, you will see the many resemblance between one system to another, between electrical circuit model and mechanical circuit. Later with biological, you can also model biological system using the knowledge from this electrical circuit model. That's why actually electric circuit analysis, like what we are learning now, as well as from semester 1, is not only useful for analyzing electrical network, but also will be useful to model other system in nature, including biological system. Okay. So we have studied here series RLC circuit, whose impedance Z as a function of J omega equals to R plus J omega L plus 1 over J omega C. We could also have a parallel RLC circuit, in which case then instead of impedance, we can express it in terms of admittance. Admittance, so which is equals to the G, the conductance, plus J omega C plus 1 over J omega L. Okay. The reactance of each circuit is 0. So when J omega, when the reactance here in this circuit is 0, means the imaginary part of the impedance is 0. So J omega L equals to 1 over J omega, equal to 1 over J omega C. J omega C here equals to negative J 1 over J omega L. Yeah, and the condition for that is that omega L equals to 1 over omega C, or omega 0, the resonant frequency, equals to 1 over square root of LC. The frequency at which the circuit becomes purely resistive, when this admittance and then this admittance cancel each other, and this reactance cancel with this reactance, then the two become purely resistive. The frequency at which those happen is called as the resonance frequency. So properties of resonance circuit, that at resonance the impedance or admittance is minimal, because the imaginary part is 0, the reactant part is 0. At impedance here, R plus J omega, the impedance equals to R plus J omega L plus 1 over J omega C, or the magnitude equals to R square plus omega L, the square of omega L minus 1 over omega C. Similarly, at admittance system, the magnitude of admittance squared equals to the conductance square plus omega C square negative 1 over omega L square. Yeah. So like that. Yeah. So here, this is the graph. Actually, we have studied in the previous slide. It has a minimum value at omega 0, when omega L equals to 1 over omega C. Similarly, admittance, it has minimum value at omega 0 when omega C equals to 1 over omega L. Current through the serial circuit or voltage across the parallel circuit can become very large. Yeah? You see here, because the impedance is minimum, and the current will be voltage divided by the impedance, right? Voltage divided by impedance according to Ohm's law in series circuit. When the impedance is minimum, very small, then the current will be very large. On the other hand, at parallel circuits, since the voltage equals to the current equals the voltage equals the current divided by admittance. When the admittance is very small, then the voltage will be very large, because the admittance is at minimum, because the omega C equals to 1. This is equals to 0, so admittance only equals to the conductance part. So the voltage equals to current divided by Y, or current will be equals to current divided by G, and then the voltage will be maximum, very large. So the quality factor here is represented as the ratio of the impedance to the resistance, ratio, or omega 0 L in this case, at the impedance at the inductance, omega 0 L divided by R, or the ratio of the impedance at the capacitance, 1 over omega 0 C divided by R. So since they are basically similar, only we deal with different parameter. If in the series it is with the impedance, while in the parallel it is with admittance, then you can basically they are the same. Resonant circuit, we will focus in the later slides on serial circuit. Okay. At resonance, the power factor is unity, because the imaginary part of the impedance is 0, so it means that then the voltage 1 here will be equals to voltage R. So here the voltage at L equals to J omega, the impedance is J omega L times I, and the voltage at C equals to negative J I divided by omega c. So this is the phasor diagram at omega equals to omega 0. Yeah, since omega L equals to 1 over omega c, then VR will be equals to the V1. Yeah, so it is the power factor will be unity because the reactance is 0. When omega is less than omega 0, this one, the Vc will be larger than VL. Okay, so the voltage is capacitive, yeah, and like this. The voltage will V1 will lag the current by a theta Z. When omega is larger than omega 0, the voltage will be inductive, yeah, since the J of I times the current times the J omega L is larger than I times 1 over omega C. At parallel circuit, like this, yeah, the current flowing, Ig flowing through the conductors here, the resistance, is G times V1. V1 basically equals to Vs here. The current flowing through the capacitance equals to J omega C times V1. And the current flowing through the L equals to V1 divided by J omega minus J divided by J omega L, or minus J V1 divided by omega L. Yeah. When now we draw the phasor diagram of current versus the voltage one. Okay, at the omega equals to omega 0, the current will be equals, the current flowing here, Is, will be equals to Ig. Yeah, here will be equals to Ig, and because it does not have any imaginary admittance. When omega less than omega 0, then this one will be IL, yeah, will be inductive current. Yeah, so the current lacks the voltage. Yeah, the current lacks voltage in similar like an inductive series, yeah, voltage. Then when omega larger than omega 0, then the current will be capacitive. Yeah, this IC is larger than IL. Okay, this is for parallel circuit. So below resonance in series, the circuit will be capacitive. Above the resonance, like this, a capacitive. Above the resonance in series circuit, it will be inductive. The network will be inductive. On parallel circuit, on the other hand, below the resonance, the circuit is inductive, while above resonance, the circuit is capacitive. Okay, based on the admittance in the parallel circuit. Okay, let's take some examples, problem examples. Determine the resonance frequency. Okay, the omega 0, the voltage across each element at resonance, and the value of the quality factor. So from the formula, the reactance should be 0, so omega 0 should be equal to 1 over square root of LC. So from here we can calculate, we can substitute L and C values into the formula. 1 over square root of 25 times 10 to the power of minus 3 Henry times 10 to the microfarad, yeah, 10 times 10 to the power minus 6 farad. Then this is equals to 2000 radian per second. Okay, then we determine the voltage across each element. The voltage across the resistance 2 ohm will be equal to the current multiplied by the voltage. Yeah. So at the resonance, the Z will be equals to 2 ohm, yeah, because the contribution from the reactances are 0, yeah, at resonance at 2000 radian per second. So the impedance is only equals to 2 ohm. Therefore, the current equals to the voltage divided by the impedance, 10 volt divided by 2 ohm, equal to 5 ampere. Then The inductance, at the inductance here, the impedance is omega 0 L, 2000 radian per second times 25 millihenry equals to 50 ohm. And the voltage at the inductance equals to J omega 0 L, the impedance, times the current. The J 50 ohm multiplied to 5 ampere equals to 250 with a phase angle of 90 degree due to this J. At the capacitance, the impedance is 1 over omega 0 C, should be equal to omega 0 L, 50 ohm also. But the voltage of the capacitance equals 1 over J omega 0 C times the current, or minus J 50 ohm times 5 ampere equal to 250, but with a negative 90 degree phase. Okay. So here the voltage across the resistor basically is 5 times 2 ohm, or 10 volt, equals to the Vs. Now the quality factor equals to 1 over R times omega 0 L. 1 over 2 times omega 0 is 2000 radian per second times 5, 200 times 10 microfarad, times 10 microfarad equals to 50 divided by 2 equals to 25. Okay, the quality factor is 25. So here at resonance, VL equal to omega 0 L times Vs over R. So here you see from here omega 0 L times the, which is here omega 0 L. This is the current, this is the current times the omega 0 L. This is the current at resonance times this one, which is the voltage at the inductance, and omega 0 L divided by R, but R basically is the quality factor times the Vs, the voltage source. And similarly, the voltage at the capacitance is equal to the quality factor 25 times the voltage source. Then this 250, right? 25 times 10 is 250. The difference is only on the phase angle. At the VL, the phase angle is 90 degrees. At the VC, or the capacitance, the phase angle is negative 90 degrees. But their magnitudes are, their magnitude is the same, 250. Okay, another example. Given L equal to 0.02 Henry, 20 millihenry, with a Q factor of 200. Now the Q factor is given instead of the value of the passive components. The Q factor is given 200, L is given. Now you are asked to determine the capacitor necessary to form a circuit resonant at 1000 Hertz. So the resonance frequency is also given at 1000 Hertz. So from the resonance frequency formula, we know with L, with Q is 200, we cannot yet calculate the L here because the resistance is not known. Okay, the resonance can be calculated. Resonance frequency here omega 0 can be calculated by 2 times pi times 1000. Okay, the Q is known, but L cannot. L is given 0.02 Henry, but R we can then calculate the R. Alternatively, we can calculate capacitor directly from the formula of resonance frequency. Omega 0 equals 1 over square root of LC. 2 times pi times 1000 Hertz equals to 1 over square root of 0.02 Henry times the capacitance. So from here, we obtain capacitance equals to 1.27 microfarad. What is the rating for the capacitor if the circuit is tested with a 10 fault supply. So at resonance, then the VL equals to the omega 0 L, yeah, Vs divided by R. This is basically the current flowing through that series circuit times the impedance, yeah, omega 0 L. And omega 0 L divided by R equals the quality times the Vs. Then similarly, Vc can be calculated from the quality factor times the Vs. So from here, then since Vs is 10 volt, the quality factor is 200. Vc equals to 200 times 10, 2000 volt. Okay, so the volt rating for the capacitor is 2000 volt. So from here, then we can also calculate the resistance from the quality factor formula. The R equals to 2 times pi times 1000 times 0.02 divided by 200. We obtain the resistance 1.59 ohm. The current is therefore voltage divided by the resistance, and volt divided by 1.59 equals to 6.28 ampere. Here, however, the reactive power on the capacitor exceeds 12 kilovolt ampere from the voltage here, yeah, times the current. Yeah, voltage here times the current is larger than 12 kilovolt ampere. Yeah. This is how many? 12,000. There is a 0.28 here times 2,000 volts, so larger than 12 kilo ampere. Okay. Another example, the R and L is values are given, but the C is not. Then the voltage is given. Find the value of C of the capacitance that will place the circuit in resonance at 1,800 radian per second. Okay, the resonance frequency is given, so we can use the formula of resonance frequency to find the value of capacitance. Omega 0 equals to 1 over square root of LC, yeah, 1,800 radian per second. So one moment, be careful. In this example, it is the resonance frequency is already given in the unit of radian per second. So if it is in radian per second, it is already in cyclic frequency. You do not need to multiply again with 2 and pi. Okay, you can immediately apply 1,800. But see the difference with the previous example. The resonance frequency is given as hertz, 1,000 hertz. So in the formula, you need to multiply that frequency with 2 and pi first, times 2 and times pi. Okay, I hope it is clear. Yeah, so be careful with the, you have to read the problem carefully in order that you can apply the correct formula. So from here, 1,800, we substitute the value of the inductance, 0.1 Henry or 100 millihenry. From here, we find the capacitance to be 1 over 0.1 times 1,800 square, or 3.86 microfarad. Now find the Q, the quality factor of the network, and the magnitude of voltage across the capacitor. The Q can be calculated by 1 over R times omega 0 L, right? The omega 0 L divided by resistance, the ratio between the impedance and the inductance to the resistance. 1,800 times 0.1 Henry divided by 3 ohm. The Q is 60. So the voltage at the capacitance equals to the Q multiplied to the source voltage, yeah, 60 times 10, which is equals to 600. Okay, 600 volt. Okay, so far clear? Any questions? No question, yeah. So I hope it is clear now. Okay, so we go to another section about the resonance for the series circuit. This we have derived earlier in the previous slide. And then the voltage gain will be the VR divided by V1. Okay, VR divided by V1. So here will be equals to 1 over 1 divided by 1 plus JQ, the quality factor of multiplied to omega divided by omega 0 minus omega 0 divided by omega. Okay, so this is basically come from this one, the voltage gain here at the resistance, yeah, R equals to R divided by the total V1 is contributed by the voltage from each of the impedance, yeah, from resistance as well as from the reactances. So R divided by R plus J omega L plus 1 over J omega C, or equal to R divided by Z, Z over Z is a function of J omega. So if we look here, the connection, if we divided each of this by R, so the upper part become 1, this one become 1, J omega L divided by at resonance, yeah, divided by R equals to the Q, yeah, JQ, and this 1 over J omega C divided by R is so equal to Q. Okay, at resonance, omega 0 L equals to QR, and omega 0 C equals to 1 over QR. Okay. This is we derived already from the previous slide. So therefore, Zj omega equals to R plus this one, yeah, this one, J omega L, J omega QR, this one, QR equals to omega 0 L. So the omega 0 here, let's see, so this is equals to omega 0 L. So this will cancel, right? So this term basically will be equal to J omega L. So the same as this part. And this part, this QR equals to 1 over omega 0 C, 1 over omega 0 C. Okay, so this will cancel. So this becomes then J minus J 1 over omega C. This is equals to this one. Okay, so this is how it is derived, yeah, this formula, the derivation of this formula. So Zj omega equals to R multiplied to 1 from here, 1 plus JQ. So the JQ terms we put into 1, and then we put the other one inside parentheses as omega divided by omega 0 minus omega 0 divided by R. Okay. And gain is R divided by Z. So therefore, the magnitude omega is equals to the magnitude of gain with the phase angle equal to the phase angle of the gain. So here, gain is VR divided by V1. So gain here equals to R divided by Zj omega, or R divided by this terms, yeah, or 1 over R cancel each other, become 1 over 1 plus JQ omega over omega 0 minus omega 0 over omega. And when we plot the relative magnitude, yeah, of the gain here, yeah, of the magnitude as a function of omega, here then it has a maximum at omega 0, and then it has this, when the value is 1 over square root of 2, because of this, then it is at omega L0 here, and as well as omega low and omega high. This is the bandwidth of the resonance frequency. Okay, and the phase is between 45 and minus 45 degree. And this is the negative arctangen of Q is 1 here. This is because this form from the imaginary part divided by the real part to have the phase angle. So this is the half power frequencies, omega low and omega high. The bandwidth equals to the omega 0 of the resonance frequency divided by the quality factor. So from here we know that when the quality factor is high, the bandwidth will be very small. The bandwidth will be very small or very sharp. When the quality factor is low, we have a wider bandwidth. Here, omega, the low frequency is equals to omega 0 from here times 1 times minus 1 over 2q plus square root of 1 over 2q squared plus 1. Okay, let's have a break. 3. And